We're just waiting for our participants to actually join in. Just a minute or so. We're about 60 or so participants now. We'll have a little bit more that's coming in. I'm sure it's good evening for most of us in Australia, but there's alumni and other non-alumni members joining us from other parts of the world. So good morning and good afternoon to you guys. Just a couple of more seconds and then we'll kick off the session. Still a few participants are joining in. I think it's slowed down a little, so. All right, let me start off the session. Look, good evening, everyone. My name is Udeshka Vijayawardena. For those who don't know me, I'm the Alumni Engagement Manager for the Faculty of Science. Let me kick off the session by paying respects to our elders and acknowledging the traditional owners of our land and welcoming all our alumni, both local and international, and other members who are non-alumni joining in. For those who are joining us for the first time, the Monash Science Alumni Webinar Series essentially is designed for our alumni to keep in touch and hear about the ongoing research work that's happening within the the Faculty of Science within the different schools. And due to popular demand, we've actually made it available for members who are non-alumni who are joining us today. And it's been quite popular. So today we've got about 400 registrations. And I mean, every time we do this webinars, we get more members joining in. So thank you for all the support. The format for tonight's event is that we'll have a half an hour presentation from Professor Peter Cawood, and then it'll be followed by a 15 to 20 minute Q&A session. So any questions that you have, just put it in the toolbox just below your video, and the questions will be answered during the Q&A sessions as much as the time permits. Today's presentation has been prepared from the School of Earth, Environment and Atmosphere. And the moderator for this evening that's joining us is the head of school of EAE, or Earth, Atmosphere and Environment, Professor Andrew McIntosh. So Andrew, if you want to turn your camera on and say hello.
Hi, everybody.
There you go. This is Andrew joining us. Now, let me introduce Andrew to those who don't know him. So Andrew is actually well recognized internationally for his research for the interactions between glaciers, ice sheets and climate systems. I mean, it's a hot topic, melting glaciers and, you know, climate change and global warming. So Andrew's right in the middle of the research of those areas. Before Andrew joined us, he worked with the Antarctic Research Centre at the University of Wellington as a director. And the centre was actually awarded the New Zealand Prime Minister's Prize last year. And it's definitely a testament to some of the work that Andrew's been doing there. Andrew currently is the chief investigator and the team leader of the Securing Antarctica's Environment Future, or SAFE, which has recently been awarded a 7-year, $36 million research program support from the ARC, or the Australian Research Council, and it's hosted at the Monash University. So we are quite happy and privileged to have Andrew here spearheading that initiative. So Andrew, I will hand over the session to you, and I'll let you give a bit of update of what the school does, and introduce Peter to the session.
Thank you very much, Udi. So good evening, everybody. My name's Andrew McIntosh. It's my pleasure to be here to give this introduction today. And so the School of Earth, Atmosphere and Environment formed about 5 years ago from the amalgamation of physical geography, atmospheric sciences and geology at Monash. We're one of the top earth science schools in the country with ERA rankings of 5 in many subjects. We've got leading educational programs in geography, environmental science, earth sciences and atmospheric sciences. Our school's a vibrant community of several hundred people, including academic and professional staff, postdocs and PhD students. It really is a pleasure coming into work every day when we're able to. So I look forward to going back to the office. Earlier this year, members of our school were welcomed to country on the Monash Clayton campus by a member of the Boon Wurrung Foundation. And we also recently appointed an Indigenous Australian, Drew Giles, to an academic position in our school. We consider such engagement essential, given Australia's Indigenous peoples have developed an understanding of the Earth over many tens of thousands of years. So we've got this legacy in the past that we're deeply connected to, but our school is also focused on the future. We aim to educate the next generation of earth scientists to find environmental solutions for society and our planet. Our motto is "The world is our lab," and our work takes us from the Earth's core to the top of its atmosphere, from the tropics to the Antarctic ice sheet. Of course, we can't travel at the moment, but we look forward to doing all these things again. And earth science is key to exploring and understanding our solar system and beyond as well. So we have a deep interest in space science too. So today, it's my great pleasure to introduce Professor Cawood, who's one of the world's most influential and highly cited geologists. An absolute pleasure to have as a colleague. So Peter's screen is on, so you can say hi, Peter.
Hi, everyone.
Peter's research focuses on the origin of Earth's continents. And you can share your screen too, if you like, Peter. I can keep going while we do this. So he integrates direct field observations with leading laboratory techniques. He's worked in regions from Archean cratons more than 2.5 billion years old to modern and active margins of the Pacific Ocean, at scales ranging from global to microscopic. He's had a great time while doing it, I know that. He's an inspiring teacher for our students. But anyway, I'm off topic. His work aims to resolve the range of tectonic processes involved in crustal formation and the feedbacks with the rest of the Earth system. And Peter obtained his undergraduate and PhD degrees from the University of Sydney. He's held academic positions in Australia, New Zealand, Canada, the UK. He's currently an Australian Research Council Laureate Fellow at Monash University, which is of course an extremely prestigious appointment, and he's an elected Fellow of the Australian Academy of Sciences and the Royal Society of Edinburgh. So it's time now for me to turn over to Peter and listen to him speak on Earth Matters, a tempo to our planet's evolution. And go ahead, Peter. Thank you.
Great. Thank you very much. Thank you, Udi, for the opportunity to speak to Monash alumni and to the broader community as well. And Andrew, thanks for the introduction. As you can see, I've had a very fortunate career and been able to see many wonderful parts of this world, not obviously in the last 18 months, but previously. And what I want to do today is really talk about some of those features. What I hope to do is really give you a journey, not to the center of the Earth, but perhaps through Earth history, and talk about how the planet's formed, how we've reached this wonderful state that we now call our home, and this environment and the resources. And but we didn't start off like that. It was quite different early on. And so it's a difficult topic to cover. I've got to cover 4.5 billion years of Earth history in 30 minutes into an audience that includes geologists and non-geologists. So I hope there's something you can draw of interest from it. If we were to ask Elon Musk to take us on a journey, whoops, we're going too fast here, then we'd go up into space and we'd look down and we'd see something like this. This is what the Earth looks like today. And you can get a bit of an image that things are happening, things are moving, the clouds are wispy, the oceans moving, of course, you know, the continents look pretty fixed and stable. But if we look in terms of the long-term history of the Earth, that's definitely not the case. Things have changed dramatically. And so if we were to ask Elon to take us back up into space a few years in the past, in fact, some 4.5 billion years, then the view we'd get would be quite different. Now, we seem to be having a delay in things moving here. Let me just see if I can get it. There we go. And it would look something like this, you know, quite different to the current environment. And so really the story that I want to present today is how we go from this initial setting to this blue-green planet we have today. Clearly the Earth has cooled through that time, and in response to that cooling, we've developed this atmosphere, the oceans and the crust that we all know and love. And what I want to try and get across is that they didn't happen independently, they're linked, and they're linked to this overall cooling of the Earth in response to its formation. And that's shown on this next diagram. That the bottom half has time on the horizontal axis and temperature on the vertical axis. And this represents the temperature inferred for the Earth's convecting mantle through time. And the current temperature we think is around 1350 degrees C. And in the past, going back to the early Earth, it was some 200 to 300 degrees hotter. And these changes have had fundamental impact on the more superficial elements of the Earth, on the crust and the superficial reservoirs, and also in controlling the tectonic environment that operates on the Earth. And there's some of the features that I want to touch on today. The modern Earth is kind of unique in the solar system. It's characterized by four features. It's got a bimodal crust, that is continents and oceans. It's got active plate tectonics. The ring of fire continents are drifting, the Atlantic opened, South Africa and South America moved apart. It's the only planet in the solar system with liquid water. All of that adds up to a life-supporting environment. How that's developed is hard to unravel from what we have preserved. And what we do have preserved are the rocks, and the rocks are where we get this story from. And in particular, it's the continental rocks. The oceanic rocks, this blue part of the Earth here, are remarkably young in terms of Earth history. They're no older than about 200 million years. Whereas the continents, because of their more felsic, lower density composition, are more buoyant, and they range back to around 4 billion years. And so it's unraveling this history from the continental rocks that I want to talk to you today about. Now, the problem is that we don't have a complete record. If we did, it might be a bit easier. And this diagram on the left tries to highlight that. You'll see that depth is on the vertical scale and time is on the horizontal scale. So the present day, we're here, this direct data point, and we can observe the oceans, we can measure the atmosphere, etc., and we can look at the rocks that are forming today, and we can make measurements, and we know the internal structure of the Earth. Unfortunately, as we go backwards in time, the record is incomplete. There are gaps. Those gaps become more pronounced, and the amount of rock that's old gets less and less as we go back to the early history of the Earth. So this Earth is it's a complex, multi-dimensional system operating across a variety of temporal and spatial scales. But as we go back in time, we have less and less information to try and understand exactly what was happening. Even given those constraints, one of the things we know is that although the mantle temperature has been cooling progressively, shown by this orange curve that I showed earlier, if we look at various bits of data or proxies for things like the biosphere, the atmosphere, the oceans and the crust, then they show a much more episodic or pulsed record. And so part of the problem is documenting those changes, but then how are they linked? Is it a meaningless disjunctive orchestra, or is there a nice tempo to what's going on? And so what I'm going to try and do is outline what some of these changes are and try and speculate on why I think they're linked, and I think they're linked due to cooling of the mantle and that change that it invoked in the way that the upper parts of the Earth, the lithosphere, the upper crust and mantle, developed over time. So actually just going back, I'm going to use this diagram a lot in the rest of the talk, and I'm going to go through the elements of it, the nature of the atmosphere, the oceans, the crust, etc. And so I'll keep on coming back to this and developing various aspects through time. So we can look at the atmosphere. It's changed remarkably since the early history of the Earth. Today, of course, we have some 20% oxygen. For the first half of Earth history, we had no oxygen, essentially. In the atmosphere, we had lots of carbon dioxide. We're worried about carbon dioxide today. It was the dominant, or it was one of the dominant components along with nitrogen in the early history of the Earth. But it's diminished considerably over the last 4 billion years or so. Those early components of the atmosphere were largely derived from degassing as the Earth cooled, the CO2, the N2, etc. But remarkably, throughout most of Earth history, it's been amenable to life. And so life, for whatever reason, and we don't fully understand, it started at some point very early in Earth history, within the first probably few hundred, 500 million years. And not only that, but early on, certain types of life formed, cyanobacteria, that could photosynthesize and thus produce oxygen. And they were an incredible invention, if you like, oxygenation of the atmosphere. And that process is really why we're here today. It's allowed the present environment to be established. But if we were to go back in space, if we were to get Elton to take us back into space and look at the Earth from a distance, it wouldn't always look like the blue-green planet we see on the right-hand side. At times, it would have looked brown and hazy, at other times white and other times green. And this reflects the changing nature of the atmosphere over time. The brown haze is because there were a lot of methane in the atmosphere at one time. Methanogens produced a lot of methane early in Earth history. At other times, we didn't always have liquid water on the surface. We seem to have had largely a snowball type Earth that was largely frozen over from pole to equator. And at other times, these cyanobacteria that were producing the oxygen had incredible blooms. We know of those today in waterways and stuff related to farming sometimes, and phosphorus. Well, the Earth had global blooms of cyanobacteria and would have had a green hue from looking from space. So the atmosphere has gone through various phases and dramatically the oxygen levels have shown two major increases, one about 2.5 or a little bit younger ago, and then one about 500 million years ago. And that latter one was significant in allowing the development of multicellular life forms, plants and animals, and really established the life we know it on Earth today. Water. We used to think the Earth, for at least initially, was fairly dry, and in fact we refer to the first 500 million years, we call that the Hadean, after Hades, hell-like. And so we thought, like the image on the left, it was a pretty unpleasant environment, but work, particularly from the Curtin Group, Simon Wilde and others in Western Australia, working in Western Australia, has shown that there's probably been water on the Earth for the last 4.4 billion years. And that's important in terms of, again, the evolution of life, providing a suitable environment for cells to form, etc. But also, the other important development has been not just the development of water, but the emergence of land above water. And yes, there would have been some initial volcanoes, etc., that formed, but really the development of large-scale continents and the impact they've had on the composition of the oceans. Erosion, weathering of the continents, the transfer of that material through rivers, through deltas, out into the oceans, has led to a dramatic changes in the composition of the oceans and provided nutrients, importantly, to the oceans for the growth of cyanobacteria and other life forms. Phosphorus, a key driver in cell growth, as we know, as I said, for farming and overuse of fertilizers, phosphorus rich and cyanobacterial blooms. Then the same in terms of development of life on Earth, and the development of oxygenation of the atmosphere was the requirement for elements to be present in the ocean that could be used. And we can do this, and we use the isotopes of strontium because they tend to be more enriched in continental material and more depleted in rocks that are derived directly from the mantle. And so we see over time, and starting about 3 billion years ago, the influence of continental material in the composition of seawater through time. And we kind of then use that to talk about when land became emergent or when continents became emergent, etc., and produced some of the dramatic changes again that we see today. It's a complex story, the evolution of the oceans. You've got the atmosphere changing, going from anoxic to oxic. That would have interacted with the surface waters. You've got material being flushed into the oceans, particularly iron-rich material from the ferruginous surface environments. And then that increasing oxygenation of the atmosphere resulting in weathering on the land, releasing sulfur to the oceans, and that changed the composition of the oceans from iron-rich to more sulfidic, and ultimately allowed the deep oceans to become oxygenated and produce the kind of ocean structure we have today. But that early history of a very ferruginous ocean is represented in the banded iron formations that are the source of all the steel we use on the Earth today. The cars, the bridges, the whatever, is derived from these things called banded iron formations, and they formed in this ferruginous oceanic environment in this period of about 1.8 to 2.8 billion years ago, just as the surface was becoming oxygenated, but hadn't yet had a major impact on the oceans themselves. And finally, the crust. We've talked about the atmosphere, we've talked about the oceans, the crust. Today, we have a ratio of about 60% oceanic and 40% continental. Undoubtedly, those ratios have changed with time. We started off with no crust, but also the elevation of the crust has changed with time. How much was emergent at any one time? That obviously impacts on weathering, and impacts on atmospheric compositions, and impacts on ocean compositions. And ultimately, this division into oceanic and continental crust reflects the tectonic processes that are happening on the Earth today. And so this is a diagram that kind of speculates on this bimodal topography that characterizes the Earth today. The old continents, most of them are kind of near sea level. We obviously get up high in places like Everest, etc. The oceans, they're mainly deep. But we probably started off with a much more unimodal type distribution of crustal materials, and progressively the continents have grown through time to the proportion they have today. We're not exactly sure how much continental crust we had in the past. Myself and others have argued that we've probably had, by about 3 billion years ago, some 70% of the current day volume. And that's much greater than what's actually preserved today. The current preserved crust that has ages of 3 or older, 3 billion years or older, is less than about 10% of the continental crust. But we had 70, probably even a little bit more. And again, those kind of numbers are important in terms of understanding the evolution of the atmosphere and oceans, etc. The crustal record itself is complex. As I said, we've got this problem of not much crust of certain ages preserved. What we do have is that continental crust contains a mineral called zircon, and zircon is highly physically and chemically stable. It tends to hang around. It's really, really hard to destroy. And that, combined with the fact that we can determine its age, we can determine its composition, has provided huge insights over the last quarter of a century or more, as we've been able to analyze smaller and smaller amounts of material. We can now analyze Here's a zircon grain. It's about the width of the human hair. And we can analyze individual parts. This part of this grain from Western Australia is 4.4 billion years old. It's the oldest piece of the Earth we know of. And we now have multiple analyses. And what's interesting is that the age distribution changes. The early age distribution, assuming that it's somewhat representative, is a fairly continuous record. Very little, progressively increasing. And then suddenly we start to get this pulsed record of peaks, troughs through Earth history. What does that mean? So we've got these records that show changes through Earth history, whether it be atmosphere, oceans, or the crust. How are they linked? How do they relate to one another? And I think the key question here is, what is the tectonic mode under which the Earth operated? As I said, today it operates with plate tectonics. Continents drift apart, oceans are consumed at convergent plate boundaries, generating explosive volcanism, whether it be in Japan or the Andes or the Philippines, the so-called ring of fire around the Pacific. And continents drift apart. Africa and South America are the key examples. You know, the early Earth was quite different. It was this magma ocean type environment in which we had magma at the surface differentiating into a core and a convecting mantle. And then most other planets in the solar system don't have plate, in fact, none. No other planets in the solar system have plate tectonics. But the Earth, and they operate under a system we called stagnant lid. They have a kind of a semi-rigid lid. There's a convecting mantle, at least in some of those other rocky planets, and they lose heat with sporadic type volcanism through that surface. But they don't have this partial convective overturn and recycling of crust that we have through plate tectonics. And so a key question is, when did plate tectonics originate on Earth? And it's kind of remarkable, really, that plate tectonics is the defining feature of the Earth today. Yet estimates of when it commenced range over some 80% of Earth history, from very early in Earth history, pre-4 billion years, to 800 million years ago. Part of the reason for this uncertainty is, again, this decreasing rock record as we go backwards in time. Part of it is the criteria that individuals use to establish what they mean by plate tectonics, or how they recognize plate tectonics in the past. And part of it is, so the integration of those two features has led to this uncertainty. So what I want to do now is try and quickly talk about when I think plate tectonics started and the reason for that, and then bring that into that picture of those evolutionary steps we've seen in Earth history. The characteristic of, or some of the characteristics of plate tectonics are that it involves the motion of plates. So here's a map of the Earth today, classic first-year geology type diagram showing the different plates. They're all in relative motion. The plates themselves are rigid, but they have deformation focused at their plate boundaries, and they're in relative motion with respect to one another. The problem in terms of extrapolating these kinds of features backwards in time is that a key feature of plate tectonics is this system of linked plate boundaries that envelop the Earth. And of course, prior to 200 million years ago, we've lost 60% of the Earth's record. All the oceanic crust has been recycled. So we only have the 40% that's continental crust preserved. We can't unequivocally establish this linked system. So we have to use other criteria. And we use things like, or what I want to talk about now, are things like, when did we find the lithosphere, the upper crust and mantle, were rigid? And do we have evidence for relative motion? Two other features that characterize it. And I think we see that the early continents of the Earth, the so-called cratons, Western Australia, parts of South Africa, parts of North America, all the major continents have these really old rocks in their core. But and those rocks have a pretty complex deformational and temperature and pressure history, and they've been melted and deformed relatively easily at times. but they also reach a point where they became stable. And by that, I mean they also became rigid. And so we see this very nicely in things like the Zimbabwe craton, where cutting across it, and here is an air photo of this same feature, we have a thing called the Great Dyke. And this formed through brittle fracturing of the whole of the Zimbabwe lithosphere. And placed through it was this series of mafic magmas. Western Australia shows a similar thing. We see these rigid, or these linear, rectilinear dikes cutting right across the Yilgarn at about 2.4 billion years. So a lot of the cratons became stable prior to 2.5. And interestingly enough, that seems to correspond with a whole bunch of changes in the rock record. And let me just go quickly through some of those. We find evidence for the first continental amalgamations. In other words, these individual cratons, whether it be Zimbabwe or South Africa or Western Australia, their histories of each of those cratons is unique. They developed largely in isolation, but we also see younger rocks in the late Archean 2.7 to 2.5 Ga that show that some of these blocks were in close proximity. They have overlapping sedimentary sequences. So we know that one, they must have been physically separated, and two, they subsequently came together. And so we see in the sedimentary record evidence for divergent plate motion, breaking apart of some of these cratons, but also the coming together. And passive margins are some of the key rocks that highlight that feature. And so the first passive margins are about 2.8 billion years ago. And they form when continents break apart, when South America broke apart from Africa, then we form a series of passive margins along its margin. Australia is surrounded by passive margins as it broke away from Gondwana. We also see sedimentary basins when continents come together, foreland basins. When India collided with Asia, then we've formed not only great mountain belts, but these foreland basins where one plate loads the other plate and depresses it, and sediments can accumulate. So we have evidence for the first foreland basins and the first passive margins all forming around 3 billion years ago. Similarly, we have a change from a relatively continuous record of zircons, albeit fairly limited, to a much more pulsed record since 3 billion years ago. We have dramatic changes in the rate of crustal growth from around 3 kilometres cubed per annum for the first 1.5 billion years to less than 1 kilometre cubed per annum for the last 3 billion years or so. And we have other changes in the atmosphere and the oceans, as I've said. And so I, and others I hope, tend to view this change as the onset of plate tectonics. And so we went from a magma ocean initially, presumably some sort of stagnant lid phase, and I'll come to that in a second, and we started to form some type of plate tectonic environment at that stage. It didn't happen overnight, it didn't happen instantaneously. Rather, it tended to take place over this extended period. You know, it probably formed locally in some continents, perhaps stopped and started, but over this period from about 3.2 to 2.5, it became widely established. And I would think formed a global encompassing system at that time. It's hard to predict, of course, because, as I said before, we don't have that early record of the Earth. And one way that we can perhaps get a hint of the way the Earth did behave prior to plate tectonics is through numerical modelling. And Fabio Capitanio and Oliver Niebel at Monash have been doing a great job in developing some numerical models, Fabio in particular. And this is from a recent paper of his, in which he starts off with a fairly stagnant lid environment, in other words, a surface on the Earth, and underneath the mantle. And these numbers here, 211 to 814, correspond to millions of years, so essentially 1 billion years of Earth history here. And what he imposes is he starts with a little bit of rifting, extension of this lid, and this invokes a dramatic change, a major perturbation in the whole system. And what happens is that thinning of the surface layer drives decompression melting, and we get dehydration stiffening of the residual material and formation, if you like, of a protoplate environment, this region shown in yellow. And it forms, and it also migrates laterally in that process. So the rift is pushing it sideways as more rigid, stiffened material forms. And as a consequence, intervening material is consumed. And as we go on, we kind of develop a pseudo plate tectonic type environment in one half of the model. But interestingly enough, in the other half of the model, we stay in what we would view as a stagnant lid, in which we have a lid. We don't form this rigid, stiffened horizon, but we do get detachments, material sinking down and being recycled under this convecting mantle. So you can imagine, if you like, the Earth could behave like this, and half of it, parts of it, could remain in this stagnant lid environment. Parts of it could remain or could become this beginning initial plate tectonic environment. And so we kind of envisage this as this early period of transferring around 3.2 to 2.5 between what had been a long-lived pre-existing stagnant lid environment to the current setting of a plate tectonic one. And I should just point out that the modelling that Fabio did was done under conditions that we think operated on the early Earth. In other words, this much higher temperature for the convecting mantle. And so this kind of environment, or this type diagram rather, summarizes those changes. The early Earth, in the Hadean, we had this stagnant lid, convecting mantle underneath, bits of material being recycled back into the mantle, volcanic activity releasing heat through the surface. But then we developed this mixed lid and plate environment. Half of it was the stagnant lid type environment, and half of it was this large scale circulation in the mantle and the development of more rigid material that was able to migrate laterally and ultimately switched to the modern plate tectonic environment. Okay, so I've gone through and talked about some of these features. I want to just very quickly now talk about how we can link that together through time. And you'll see, so here are these features on the Earth, and you'll note that in the top of the diagram, I've given it various names: the early Earth, the youthful Earth, middle age, contemporary Earth, etc. And I've said that, you know, there's a plate tectonics after 2.5, and there's a pre-plate tectonic and a transitional mode prior to that. So we started off, and I'll go fairly quickly now because I can see time is running away from us, with an initial magma ocean, a fairly inhospitable environment, added to by the fact that we had widespread meteorite impact slamming into the Earth for the initial part of its history. We then developed the early continental fragments, highlighted by such as the Pilbara region in Western Australia with its dome and keel structures, big granite round domes with keels of mafic rock in between, very spectacular from the air. It was largely a water world. These continents were largely submergent. They started to become emergent, but their volume in terms of the overall continental volume was relatively low, but they provided environments for the development of microbial life, as well as photosynthesis. Through this transition period, we started to see dramatic changes in Earth history. We started to see emergence of continents reflected in the changing composition of seawater. That would have provided important nutrients to the oceans, which ultimately stimulated further these cyanobacteria, allowing for the oxygenation of the atmosphere. We started to see evidence for lateral motion of continents in that time frame. And then we really start with a plate tectonic environment. We see major amalgamation of continental masses. You've heard of Pangaea, Well, we think the first real supercontinent was a thing called Nuna that formed about 2 billion years ago. And with that, we were able to have major influx into the oceans, major weathering, impact on the atmosphere, etc. Interestingly enough, we have a period that we kind of say was a stable phase. Some people have called the boring billion. It's 1 billion years of Earth history. It's probably because we don't know enough about it. I doubt it was boring. It was undoubtedly quite dramatic. It's bookended by 2 supercontinents, the formation of Nuna I've mentioned at around 1800, and the breakup of the next supercontinent, Rodinia. And in fact, it was probably the Nuna never really broke up. It just grew further blocks onto it to form Rodinia, and then that ultimately broke up, and we reached this current phase, the next period of oxygenation of the atmosphere, development of large-scale multicellular organisms, and the processes that operate today were essentially operating then. That change was in part driven by a change at 800 million years in the way subduction, the way plate tectonics works, with continuing cooling of the mantle. The mantle now was only some 80 degrees or less than it is today. And that allowed for the dragging down of continental fragments deep into the mantle to form high pressure, ultra high pressure mineral assemblages. And we start to see them, this is not a very good diagram, I'm afraid, these blue dots on the diagram come in at about that time. So it's a complex multi-dimensional system that has interacted over billions of years across a variety of spatial and temporal scales, but we still have this fundamental question of how the early Earth operated. Numerical modelling is one way to find out how it worked. And I'll just finish off by saying that some of the other planets, Mars in particular, may provide some insight into that history. And that's because Mars has been largely, nothing much has happened for the last few billion years. It was active early on. We know that in terms of our understanding of the geology of Mars, and this is kind of a simplified geological map. But the important thing is the brown areas in terms of the early history of the Earth, because they're of a similar age. And so they may provide a record of the processes that have now been lost on the Earth. Of course, the younger parts of Mars are some of the more interesting ones in terms of the Perseverance rover has recently landed in this region where we have good evidence for water flowing into a basin, and hopefully we'll find out more. So yes, there was water on Mars. Whether there was life, I think, is another question. And we've only got to see how difficult it is to understand the early history of the Earth. We have some rocks preserved, but we argue about whether what we see in them is life or not. And so you can imagine doing this remotely from another planet is going to be equally or even harder in that study. This is just a diagram to compare the histories of Earth and Mars over the last 4.5 billion years. Whereas Earth has been dynamic, has maintained a liquid ocean, has maintained an atmosphere, Mars has largely lost those features. Earth has maintained them because of the dynamic nature of plate tectonics, which has allowed for regassing of the atmosphere and the oceans. Whereas on Mars, we've kind of lost all that subsequent atmosphere and oceans that may have been present. But the beauty of that from a geological perspective, of course, is that it preserves in a rather pristine state this very early history. So let me finish up. The Earth is an incredible story of how it's evolved from this molten mass when it first formed as the planetesimals of the solar system and the sun accreted to where we are today. It's an amazing place, and it's really, you know, it's our forever home. We have lockdown at the moment. Well, Earth is the ultimate lockdown, where Elon Musk might want to take us elsewhere, but in reality, we're going to be on Earth, the majority of us, for the foreseeable future. And so we need to look after our home, but we also need to understand it. And the School of Earth, Atmosphere and Environment is what its aim is, to understand the Earth today, tomorrow, but also in deep time. Thank you very much.
Thank you, Peter. Thanks so much for taking us on that journey through the history of the Earth, and particularly of the cratons, but I thought fascinatingly of planets as well. Look, there's a number of questions. You've provoked a lot of interest, but I'll just pick a few of them. I can't ask all of them, unfortunately. There's one question here that I thought was quite interesting. So Venus and Mars are kind of the early analogues of the Earth in some way or another, and they don't have plate tectonics. Then do they look a little bit like the expanding Earth theory of Carey, the famous geologist?
Good question. I'm just trying to go back, if I can even, to that. The short answer is no. Carey, of course, so for those of you that aren't familiar, Sam Carey was an Australian geologist. He started off at the University of Sydney. He was the foundation chair at Tasmania. Interestingly enough, I kind of sidelight here, during World War II, he was a paratrooper, and he used to jump out of planes and collect, and I think that perhaps that was his interest in studying the Earth, I don't know. But his view was that the Earth had in fact changed dramatically in size. It started off as quite small, and then it progressively expanded. So he kind of had half of plate tectonics. He accepted mid-ocean ridges and continents drifting apart, but he didn't accept that material, the oceanic crust, is recycled back into the mantle, to put it simply. We all know that's wrong, or most people think that's wrong, but there's no evidence that the other planets have changed and the consequences that that would invoke. In other words, yes, there is volcanic activity on the other planets. There is possible evidence for material moving laterally apart, but there's also, with that volcanic activity, it's a two-way street. Material comes up and it may not go down through subduction zones and sinking of oceanic lithosphere as we know it today, but these other modes of stagnant lid, and they're shown here, involve things called drips or major scale delamination of the lithosphere. So although we may be producing crust via volcanic activity, material is also being recycled in those environments back into the mantle.
Thanks. So I'll move on to another question. This one is about the Earth's magnetic field. And the question is, was the magnetic field of any impact on the start of plate tectonics or nothing to do with it?
Really good question. Probably the answer is no. We've always had a magnetic field from very early on, and there have been some studies done, and I can't remember the details, but some of them are on zircons from the Jack Hills, in fact, these very old zircons, and they're able to show that there was a magnetic field early in Earth history. Of course, those that argue for plate tectonics since the Hadean may say, well, that's evidence that the two are related. But no, there does seem to be a magnetic field early in Earth history. The major change that's happened with the internal structure of the Earth is that a lot of the magnetic field, as you know, is driven by convection in the core, this iron-rich part of the Earth that formed very early on as we had this magmatic body accreting out of the solar nebula. The heavy parts sunk to the middle, which is the core, which is the iron-rich material. And what's happened, of course, is that over time, the core is actually crystallizing. And so when it first formed, it was probably all molten, and we didn't have an inner core. But at some stage, and there is a lot of debate about when the inner core formed, and the estimates vary, but it's kind of 1 billion years plus or minus 500, and that's how poorly we understand it. But somewhere around 1 billion years ago, perhaps a little bit older, the core started to crystallize, and that also did have an impact on the circulation patterns in the remaining liquid core. But no, the magnetic field has probably existed for most of Earth history.
Thanks. Hey, look, it's quite hard to choose between all these great questions, but I have to do it. So here's another one. Starts off with a compliment. Thanks, Peter, for a wonderful talk. Since we believe that plate tectonics began on Mars, why did it stop? And where do you see your future research going?
Right. Plate tectonics, there is disputes on Mars about plate tectonics and how, if and how long it may have operated. I would say the majority view is that it didn't operate in the sense of a globally linked system. And the reason for that being is that we've got very old parts of Mars preserved in that geological map I showed. The southern half of Mars is basically, from the cratering record we know, is 4 billion years plus or minus type age. There are parts, though, that do show evidence for extensive igneous activity, possible rifting, possible convergence between material. In other words, compressional structures and divergent structures. So we see evidence for local type features, but it was very much episodic and physically localized, spatially localized as well. Where do I see my future research going? Good question. Whatever takes my interest in the next decade or so, I suppose. I think there's a lot to do still on this early Earth. I think whether I do it or others is another matter. As I mentioned, people like Fabio Capitanio and others, PD, a postdoc, and students who are doing numerical modeling and doing wonderful things. They're providing great insight, not only into the early Earth, but into other processes that more recently that operate on the Earth. So I think that's going to be a key driver. I hope that I can contribute to those discussions. I suppose my strength, and perhaps those photos at the beginning showed me in lots of nice places around the world. And that's because I like field work. My legs aren't quite as good as they used to be at going up mountains, but I've learned a lot from looking at rocks, and I recommend to all of you in the audience the importance of going out into the field and making observations. That's really a ground truth, and I hope I can bring that ground truth to the numerical models, to the isotopic analyses of rocks, etc., and things. Let me rephrase the question and say, if I was starting out today, what would I do as a geologist, or what would I be doing? And I have to say that, like many people, I'm probably going to get into trouble from my colleagues for saying this, the modern Earth and the problems that it's facing, the environmental issues, are pretty important, but not pretty important, they are important, and they're pretty important problems. And so they're important. But I still like the early history of the Earth. Look, it's fascinating. It's what gets me out of bed of a morning. I worry about how these things work. These problems of bias in the record. We only have very small amounts of the early Earth preserved. What's that telling us? Is it representative? Is it something special? Is it telling us about a special process that operated, or is it telling us about, the run-of-the-mill type process that operated 3.5 billion years ago? They're really important questions. It's certainly telling us about something that happened back then, but how you view that data is important to the interpretation you then place on it, and they're things that we need to worry about more.
Thanks. Look, there's great merit in following these intellectual journeys to answer fundamental questions about our planet. So it's great to hear about that fundamental interest. Actually, in the chat, which you won't get to see the Q&A, there are actually a number of questions about more practical aspects of this as well. So, in terms of things like gold mineralization in different provinces that line up and what have you. But anyway, we won't have a chance to go there tonight. I would just like to ask one last question, which I thought was quite an interesting one. And you've talked about numerical modelling, but somebody said, what kind of statistics do people use in your field, Peter? Like, do geologists use statistics as a tool to understand the Earth?
Absolutely. Obviously, if you're out in a rock, if you're out in the field and you've only got one rock that's 4 billion years old, then statistically, this is this problem of how, what is it telling you? But in reality, one of the great advances have been in data collection, data analysis, big data in the earth sciences. The Earth is a lot of data. So it's the ultimate big data, really. And so, yes, statistics are incredibly important about and how you treat them and ignoring them at your peril, I would say. I reviewed a paper this morning for a journal which was talking about mining big data and the problems of people just indiscriminately picking it out, not looking at the statistics on the age data that they were using and drawing conclusions from it. And these are some high-powered papers that have been published in Nature, etc., without looking at the errors on their age data, for instance, and things, and how that can impact. So yes, statistics are important. The analyses that we do in the labs on elemental abundances in rocks, on isotopic ratios in rocks are all governed by statistics and making sure we have valid we have limits on the data, and when we know what those limits are and what that means for our interpretations.
Thanks so much. We're out of time, so let's
Can I just say perhaps if those that had questions and I didn't get a chance to answer them, if you want to email me at Monash, please feel free, and I'm more than happy to try and respond.
Thank you.
Thank you, Peter and Andrew. That was a great session. I mean, there's a number of questions that are still unanswered. I think, obviously, Peter, I might forward these questions to you, and if you want to respond to me, I'm happy to disseminate it with the participants who asked the questions. Yes, we've only gotten through about 4 or 5, and we have 15 plus questions on our the Q&A section. Look, thank you everyone for joining in this evening. I hope you all had a insightful listen to Peter. And what I would request our alumni to do is I will send a post-event feedback survey to respond so that I can actually gauge if these sort of talks are relevant to you, and also understand what sort of other topics are of interest to you as well. And with all the participants and anyone who's registered for this webinar, I will share the recording of the whole webinar. So feel free to share it with your colleagues or anyone who's interested in these topics. So thank you everyone, and thank you Peter and Andrew for a fantastic evening. Have a good night. Thank you.
Good night.